The industry standard for creating AI characters involves feeding a language model a list of adjectives, words like brave, paranoid, or helpful. This descriptive architecture produces three distinct failure points. It is non-deterministic, generates significant computational overhead, and remains virtually undebuggable because it lacks explicit mechanics to correct a hallucinating NPC. The Synthactor framework treats labels like brave as secondary outputs. The causal engines of behavior are the underlying control loops. Personality emerges from the interaction of these stacked, error-correcting operational loops. In this model, system state and real-time thermal constraints dictate every line of dialogue and every action an agent takes. Managing thousands of coherent entities in a single shared world requires the mathematical precision of generative control theory. This framework relies on logic developed during the 1980s. The severe memory scarcity of early microcomputers forced developers to utilize explicit states and deterministic transitions. Programs running on the Commodore 64 had no room for abstraction. Every operation had a specific computational cost, and every branch was absolute. The Usborne Firmware Extraction Protocol, or UFEP, translates these ancient constraint patterns into modern behavioral libraries. A Class 1 agent represents the baseline of this system, governed entirely by a single, isolated operational loop. We can examine this through Astronaut Firmware, a loop class derived from early spaceflight trajectory games. The Astronaut Firmware cycles through 4 phases: estimate, fire, measure, correct. It evaluates state at a tick unit, monitoring an arrow signal to trigger corrections. While the signal remains within a threshold, the agent stays in its comfort zone, operating steadily without corrective action. The firmware uses default questions to evaluate itself. The astronaut loop constantly monitors its own status, asking, what is the delta between predicted and actual, and do I have enough reserves? This continuous self-evaluation is the idle tick. Even when the agent isn't speaking, it is building a world model through these internal prompts. Applying these rigid constraint loops produces deterministic behavior. It replaces the approximations of modern AI with a system that is mathematically provable. Beyond internal logic, we must account for how a loop behaves when it encounters environmental and computational stress. Because processing power is finite, the system treats language as the thermodynamic exhaust of the loop stack. Wattitude serves as the metric for this relationship, tracking real-time coherence per watt and the literal computational load on the runtime. This gauge maps wattitude across 4 thermal zones: cool, warm, hot, and critical. Each band dictates nuanced output capacity. Rising stress triggers regression. Instead of an arbitrary angry state, the agent sheds complex surface behavior, falling back to simpler firmware logic. This regression happens instantaneously. The moment a load spike hits the system, the agent prioritizes stable baseline behavior. Recovery is slower, governed by hysteresis. The agent requires a sustained period of low computational load before it can re-engage its higher-level loops. At 100% load, the system hits a ROM fallback state. The agent drops all complexity and reverts to its most stable emergency commands. Using Wattitude to predict these failures provides mathematical predictability, eliminating the need to write endless dialogue trees for hypothetical edge cases. To create more complex agents, we move from the single loop of a Class 1 entity to the composite structure of a Class 3 agent. Archetype calculus allows us to build recognizable human roles by stacking these isolated loops on top of one another. We build a POTUS archetype using a 3-layer stack. The surface layer uses naval firmware for positional dominance. Below that, the tactical layer employs spy firmware for threat awareness. The stack completes with a survival layer of astronaut firmware, calculating resource trajectory. Input must pass through all 3 layers simultaneously. The agent is forced to balance competing priorities: dominance at the surface, secrecy in the tactics, and resources at the base. The blending of these competing logic sets creates interference patterns. This interference produces the final dialogue exhaust that the player actually hears. Because this process is deterministic, we can reverse it to diagnose an agent's internal stack. If a CEO archetype stalls on execution confirmation under stress, we can identify actuator firmware as the baseline survival layer. Engineers compile these complex archetypes through strategic loop interference, removing the need for manually authored character scripts. We have followed the architecture from the logic of 1980s microcomputers to the multi-layered interference of a modern archetype. This entire behavioral profile is stored in a single structured file, the .synth JSON. Because the behavior is engine agnostic, this file can be dropped into Unity, WebAssembly, or custom runtimes without changing the agent's behavior. This efficiency allows developers to run 1,000 deterministic synth actor entities for the same computational cost as a single LLM request. Robust agent architectures do not require us to simulate the mysteries of human psychology. Stability in synthetic agents comes from the rigid, proven mechanics of computing history. The future of interactive worlds depends on these deterministic control systems, replacing the hallucination of descriptive AI with genuine compiled behavior.